Today we will be discussing about the geometric interpretation of linear regression. In the earlier lectures, we had derived the normal equations starting with the following points. We said that the errors we get from our models, they should be small. The errors that we get on each point is epsilon I. We said that they should be small, which can be encoded in various ways. One of which is we minimize summation epsilon I squared, or minimize the L2 norm of the square of the L2 norm of the epsilon vector, or we could also minimize the L1 norm, which is summation magnitude of epsilon I, and we had started with y equal to x theta plus epsilon, where epsilon is a vector, and our objective was to learn theta. We said if epsilon is the vector containing the individual errors, the residuals, epsilon transpose epsilon is the same as summation epsilon I squared, and we had done a bit of manipulation here to ensure we have terms which are independent of theta, linear in theta, and quadratic in theta. And then we did the derivation of this quantity. We found out the gradient with respect to the theta vector of the scalar. Epsilon transpose epsilon is a scalar, and we found out, we set this quantity to 0 to find the minima, and we found out theta hat equal to x transpose x inverse times x transpose y. Today we will take a geometric view of this derivation and see if we can come up with the same result or not. We first discuss a bit of mathematical background required to understand this. We already know what a linear combination of vector means. Let us say that we have a few vectors v1, v2, v3 till vi. These are d-dimensional vectors. We can say that a linear combination of these vectors is of the following form: alpha 1 times v1 plus alpha 2 times v2 plus so on till alpha I times vi, where each of these alpha i's are scalars, or in this case just real numbers. Now there's another related definition, which is the span of a set of vectors. We say that if we have such I vectors in d-dimensional space, each vector is a d-dimensional vector, we say that the span of v1 through vi is denoted via this notation, span of this set of vectors. So this is all the set of vectors which can be generated by the linear combinations of v1, v2 till vi. So thus the span definition is dependent on the definition of linear combination of v1, v2 through vi. We'll be now using this definition for a few quick examples to ensure that we understand the concept. Or before we do that, let's take another way of computing the span of a set of vectors. Now this is a more computationally efficient or the way you may encode this in a program. So let's say that we have these vectors v1 through vi. We can encode them as columns of a matrix V, and then the span of v1 through vi is given as v times alpha, where alpha is I-dimensional vector now. So alpha is this vector corresponding to alpha 1, alpha 2 till alpha I. So this is an efficient way of writing in a matrix vector product, of writing the span of a set of vectors. So first write the set of vectors as a matrix. You put these vectors as columns of a matrix, and then you multiply that matrix with a vector alpha to get the span, where if you have considered all possible alphas, you get the span of the set of vectors. Let us now take a simple example. We have two vectors 1, 3 and 2, 1. We can see that the blue vector represents, in the x direction it's 1, in the y direction it's 3. There's another vector v2, in the x direction it's 2, in the y direction it's 1. The question for you, and you should pause at this minute, is to think what is the span of these set of vectors. Assuming you stopped, I'll go ahead and show one such combination of such vectors. So if you have alpha 1 equal to 1 and alpha 2 equal to 1, we can generate a new vector v3, which is shown in green, which is v1 plus v2. But if we had chosen alpha 1 equal to 1 and alpha 2 equal to minus 1, we could have generated another new vector v4 shown in this yellow color, which is v1 minus v2. Now with this background, can you think and let us know what is the span of the set of vectors 1, 3, 2, 1? You might have already guessed that the span of vectors would be the entire two-dimensional space. There is another way, another computational way to find out the same. So I'll show some code which I use to generate these plots. I highly recommend to yourself also create such codes. It gives you more confidence in understanding the machine learning concepts that you're learning. So I created two vectors A, B. I specified the origin. The vector which I created was in Matplotlib, it's done using the plt.quiver. So this was the first diagram that I created. Then I wanted to show how to add and subtract. So v1 plus v2, v1 minus v2. It's a simple addition. So in this case, I'm just using currently tuples. But if I had directly used NumPy arrays, I could have directly done a plus v and a minus v. And then I showed these combinations. So a couple of slides back, I mentioned that we can encode the span. We can write the span as v times alpha, where v is the matrix formed by stacking the different vectors as columns. So that's what we will do currently. We had the first column A, or first vector A, which was 1, 3, and the second vector as 2, 1. So I'll create two NumPy arrays corresponding to that. I will put the first vector, A vector, as the first column and my second vector as the second column, and thus I'll create a matrix. So that matrix looks like now 1, 3, 1, 2, 3, 1. So the columns represent the first and the second vector. And I wanted to show the v times alpha matrix vector product to give you the span. So let's say that if I have a vector, if I have a matrix, AB matrix, and I have the vector alpha, and if I do their matrix vector product, I will get the new, I'll get a new vector. In this case, it's one potential vector I can get by a combination of a specific alpha. So let's say if I had chosen alpha equal to 1 and minus 1, this corresponds to 1 times v1 minus 1 into v2, or which is v1 minus v2, which is minus 1, 2 vector, which we had already plotted as v4. So if we saw the slides, v4 was v1 minus v2. Now I was showing that we can computationally just simulate and understand what the span might be. So what I'm saying is that for alpha 1 equal to 1 and alpha 2 equal to 1, you got one combination. But let's say that you uniformly, or you using some scheme, you generated a lot of combinations of alpha 1 and alpha 2, which is, let's say, exhaustive. You try to make it exhaustive. Of course, you'll never be able to do that. But we try a lot of combinations, and then we plot all the possible generated vectors. So in my case, I am generating some numbers from the uniform distribution between minus 3 and 3. I'm generating 10,000 such numbers of size dimension 2, because I need both alpha 1 and alpha 2. And then I call this routine new vector, which does the matrix vector product. If I do this and I plot for my AB matrix, which was 1, 2, 3, 1, I get a 2D space which is almost full. If I had in fact increased the number of points, so let's go over these quickly. I was currently doing 10,000 points, and this is how my plot was looking like. It's fairly dense. If I increase that to, let's say, 20,000, you may see that now it seems I've covered the entire R2 space. If you were to increase this further, you will see that it gets only denser. So now it seems even more possible that I've covered the entire R2 space, which is to say that in a simulation way, I've shown that the span of each set of vectors is the entire R2 space. We'll now look at another example. So I want you to take a pause and think about the span of these set of vectors 1, 2 and 2, 4. So if you've thought about this, you may conclude that using these two set of vectors, we firstly notice that in these two set of vectors, the second dimension is always 2 times the first dimension, which means that any weighted combination of these that we take, we will never have a scenario where, say, the first dimension is 3 times the second dimension, or the second dimension is, let's say, the 3 times the first dimension, or 4 times, or any times, because we always have the relationship that the second dimension is 2 times the first dimension, irrespective of the weighted combination that we'll take, which would mean that the span of these set of vectors will not be the entire R2 space. So you have to think what that space might be. If you've thought about it, you'll be able to conclude that it's y equal to 2x line, because whatever combination you'll take, you'll always have the y'th component be 2 times the x component. We can also verify this using the same simulation that we wrote. If I have the A vector 1, 2, B vector 2, 4, and my AB matrix first column is the first vector, second column is the second vector, and if I am to then use the same code to randomly generate alpha 1 and alpha 2, I will be able to see that all of my newly generated vectors only lie along this line y equal to 2x, which is to confirm our hypothesis that the span of these set of vectors is a subset of the R2 space given by y equal to 2x line. Now we'll extend this concept from 2D to 3D, and this is a question for you to think. I want you to find the span of the set of vectors 1, 1, 1 and 2, minus 2, 2. So if you have looked at the pattern which we used in the previous example, you may again see that in these two vectors, the first and the third dimension are the same, which means that if you take any weighted combination of these two vectors, you will always have the third dimension equal to the first dimension. Now you can mathematically go and do regressively show that you'll have the locus or the span of the set of vectors equal to x equal to z, or you could just make a simple observation in this case and conclude that it's x equal to z, because the y can vary, but x will always be equal to z by whatever weighted combinations that we take. And this is being represented via this 3D plot. So x equal to z is this plane. So you can notice that as the x is increasing, as the x increases, proportionally z also increases for any set of points. And you can also notice that y can take any values, but irrespectively z will always be equal to x. In this plane, I have now plotted these two vectors 1, 1, 1 and 1, 1, 1 and 2, minus 2, 2. As you'll notice, or as you'd expect, the span has to contain the vectors for which we are creating the span. So therefore, these vectors have to lie in this plane. To show you the code which generated this, I'll not go in the details, but essentially it's the same our old friend mesh grid which I showed a couple of lectures earlier, and we are creating this plot surface calling xyz. We are marking the origin. We are also making arrows via quiver. So this gives us this plane which is x equal to z. Now let's take this a step further. Let's now think why I would have given you this specific kind of a data. The first column is all ones. Have we seen the first column of ones anywhere, especially in linear regression? So take a pause, think about it. So if you thought about it, you will remember that we create a column of ones, which is to ensure that, which is a way to capture the intercept term or the theta naught term. So therefore, this whole setup which I previously gave you was a part of a bigger problem where we wanted to do linear regression. So we had our data x and y. So data originally was just 2 minus 2, 2. But because we wanted to learn a theta naught, plus a theta 1 kind of a term. So therefore I also added this column of ones, and I have my y equal to 8.957.6130 1.7761. So our goal is to learn y as a function of the inputs. The input is 2 minus 2, 2. In order to do that, if you remember, I create a column of ones. So therefore, in this problem setup, what we are trying to do is to learn a theta such that y hat equal to x theta, which is our estimate on the training data, such that y minus y hat, the L2 norm of this is minimized, or the square of the L2 norm is minimized. So y minus y hat, L2 norm of this is also the epsilon vector. Y minus y hat is our epsilon vector. We are trying to minimize its L2 norm, which is what we have already seen earlier. So what we just saw a few minutes back, if we look at two vectors 1 1 1 and 2 minus 2 2. So in my matrix X, if you notice, I have stacked them up. If you stack up the vectors for which you're trying to find out the span, and now this becomes the matrix X. If you multiply that with the vector theta, where theta takes real values, so it's a R2 vector. So if we do that, then we can write x theta as the span of our columns, of these columns 1 1 1, 2 minus 2 2. Right. So after that, our goal is we want to find out a y hat such that y minus y hat is the epsilon vector's L2 norm is minimized. But here we have a very specific kind of a constraint. We can't have any y hat. Our y hat is x theta, or which is the span, which means that we can only take we can only have a restricted set of values in which our vector y hat can lie. Very specific planes or very specific locus it can belong to. You cannot artificially create any possible space. So our y hat is the span of these vectors. So this is our first vector 1 1 1. The second vector is 2 minus 2 2. In general, if we have d-dimensional data, y hat is the span of the first column, the second column, the third column, and the dth column. If we continue on this line, we are now going to plot in order to make the problem now more approachable. So we had earlier plotted our x1 and x2 vector, which is my blue vector is 1 1 1, the first column. My red vector is the second column, 2 minus 2 2, and my y vector, which is the variable I'm trying to predict, is now plotted as the green vector 8.89, 0.6, and 1.7761. So what we now know is that if we have stacked at x1 and x2 and multiply that with theta, that is the span, that has to belong to this blue plane that you are visualizing, that you are seeing, which means that x theta, any solution that you get in x theta or any vector that you get by multiplying x and theta, has to be in this plane. So this is one such y hat which I have plotted. This is in fact the most optimum one which I have plotted, which is the best y hat for this kind of a problem. So our goal is to find out a y hat in this entire plane, which is as close as possible to y. And I've plotted one such y hat, which I believe is the closest one. One such way to notice the closeness is that the y dimension is matching, and there is some difference in the x and the z dimension. But again, you can notice that y hat had to belong to the z equal to x plane, which is the span of these set of vectors. So thus you can see that the first dimension, x dimension, is equal to the third dimension or the z dimension. So y hat is one such possible vectors. There could have been many such vectors. So now what I'm showing is that in my yellow is shown the y hat vector, which I told you is the optimum, and I had shown you the green vector. Now the definition of optimum is that when y and y hat are the closest, or what we said is that the norm of the y minus y hat vector is the smallest. This occurs when the the pink vector, which is the epsilon vector or y minus y hat vector, is perpendicular to the plane. So that's when these will get closest. If you were to, let's say, take the yellow vector slightly further, you can always see that the pink vector that you'll get will be larger in length. So the smallest pink vector that you can get would be obtained when the epsilon vector is perpendicular to the plane, and it is, in this case, because of the way I've drawn, it is going to match. Like, I can show the vector sum of the y hat vector plus y minus y hat vector equal to the y hat vector plus y minus y hat vector equal to the y vector. So what we're saying is that y minus y hat vector is perpendicular to each of the vector x1 and x2. So this is happening because they are lying in the plane. So any vector which lies in this plane, the pink vector that I've purposefully chosen here would be perpendicular to both the x1 vector as well as x2 vectors, because these are vectors in this plane. So therefore xj transpose times y minus y hat should be 0. To understand this better, let's go back to the code. This is the code I showed for plotting the span of the vectors of x1 and x2. I then also had this code where I am showing you all these vectors, but importantly I am showing you some important calculations also here. I have created my X matrix. The first column of X matrix is A, the second column of X matrix is B. So A was this vector 1 1 1, B was the vector 2 minus 2 2, and my Y vector is the vector which I am trying to regress. It's my observed vector, which is 8.89.61, 1.7761. Once I created this X matrix and I have printed it, so it's 1 2 1 minus 2 1 2, which is what we have seen. Now I can use so in this case I'm doing the other way around. I'm first showing that this is the optimal solution and then plotting it. So I can find out the optimum theta via x transpose x times x transpose y. If I do that, I get a theta vector of 2.97, 1.18. If I plug that theta vector, the optimal theta vector, and I find out my y hat as x into theta, I find out my y hat to be 5.33, 0.613 and 5.33, which is the y hat vector I've plotted in yellow. Now I'm also showing the perpendicular vector or the epsilon vector. So I can call this the epsilon vector. The epsilon vector which I got is y true minus y hat, which if I print is the vector 3.550 and minus 3.55. Now what I'm saying is that this perpendicular vector, this pink vector, is also perpendicular to the first vector, which was 1 1 1, and I can verify that by doing perpendicular vector dot product with the first column, and I get a quantity which is almost 0. So this is just numerical issues, but otherwise this perpendicular vector, this pink vector, is perpendicular to 1 1 1, and you can very easily verify that also. So let's, without actually doing the calculation. So our first column is in the matrix X is 1 1 1, and our perpendicular vector is 3.6, let's call it 3.60 and minus 3.6. So if you do a dot product of these, or if you think of this as a matrix product and accordingly just adjust for the dimensions, you'll get 3.6 plus 0 and minus 3.6. So therefore the perpendicular vector dot product with X matrix would be 0, which means perpendicular vector and X matrix, this 0, the first column of X matrix is 0, which means both these vectors are perpendicular to each other. We can verify this for the second column also. So perpendicular vector is perpendicular to the second column also. The second column was 2 minus 2 and 2. So thus we have verified that our our y minus y hat, this is the epsilon vector. This is perpendicular to each of the columns that you have obtained, each of the column for which you were trying to find out each of the vector for which you were trying to find out the span, which is equal to each column in the matrix. If you write this in a more efficient fashion, you can write this as x transpose into y minus x theta equal to 0. Writing more efficient, I mean writing it in a vectorial way, which you can also see here. If I do x matrix transpose multiplied the matrix vector product with the epsilon vector, you will get the same minus 1.33 minus 2.6, which is almost both of them are 0. So what we have obtained is that x transpose into y minus x theta should be 0 for the optimal solution, right? So we've said that the optimal vector is the one where this epsilon vector or y minus y hat vector is perpendicular to each of the vector lying in the span, which I get it as x transpose into y minus x theta. So I am encoding y hat as x theta, writing y hat as x theta. So x transpose into y minus x theta is 0, which if I expand, I get x transpose y equal to x transpose x theta, which if I solve, I get theta hat equal to x transpose x, the whole inverse, times x transpose y, which was the same solution which we obtained using the normal equation method a couple of lectures earlier. But this was to show two different perspectives of deriving the same normal equation solution.